Welcome! In this session, we'll dive into an exciting problem from LeetCode, problem number 103, binary tree zigzag level order traversal. This is a fascinating tree traversal problem that challenges your ability to think flexibly about data structures. Let's explore the problem and uncover an efficient solution together. In this problem, you're tasked with performing a zigzag level order traversal on a binary tree. The idea is to traverse the tree level by level, but with a twist: the direction of traversal alternates with each level. For example, at level 0, you traverse from left to right, but at level 1, you switch to right to left. This alternating pattern continues for each subsequent level. The input to the problem is the root of the binary tree, which is represented as a tree node object. The output should be a list of lists, where each inner list contains the values of the nodes at a specific level, ordered according to the zigzag traversal pattern. Let's look at some examples to understand this better. In the first example, we have a binary tree with 3 levels. At level 0, we traverse from left to right, so we get 3. At level 1, the traversal direction switches to right to left, which gives us 29. Finally, at level 2, we alternate back to left to right, resulting in 15, 7. Combining these, the output is 3, 29, 15, 7. In the second example, we have a single node tree. Since there's only one node, there's no need to alternate directions, and the result is simply 1. These examples illustrate how the traversal direction alternates depending on the level. Now, consider the third example. Here, the binary tree has 2 levels. At level 0, we traverse from left to right, so the result is 1. At level 1, we alternate to right to left traversal, which gives us 3, 2. The final output is 1, 3, 2. This example reinforces the idea that the traversal direction alternates with each level. Moving on to the constraints, the number of nodes in the tree can range from 0 to 2000, and the value of each node lies between -100 and 100. These constraints ensure that the problem can handle both small and moderately large trees. When solving this problem, there are several edge cases to consider. If the tree is empty, meaning the root is null, the output should simply be an empty list. For a single node tree, the output will be a single list containing just the root's value. If the tree is skewed, with all nodes either to the left or to the right, the output will still follow the zigzag pattern, even though it will resemble a straightforward level order traversal. Key observations include alternating the traversal direction based on the level, with even indexed levels moving left to right and odd indexed levels moving right to left. A breadth-first search approach works well for this, and reversing the traversal order for odd levels can be done by using a stack-like structure or by reversing the node values after processing the level. To solve the problem of traversing a binary tree in a zigzag level order, we considered a few approaches. The first is the brute force approach, where we perform a level order traversal using a queue and manually reverse the order of nodes for odd-numbered levels. The process involves traversing the tree level by level, appending node values to a temporary list, and reversing the list for odd levels before adding it to the result. While this approach is simple to understand, it has significant drawbacks. The repeated list reversal adds unnecessary overhead, leading to a time complexity of O(n) squared for large trees, which is inefficient. Additionally, it requires O(n) space for the queue, making it less optimal for larger datasets. To address these inefficiencies, we explored an optimized approach that eliminates the need for repeated list reversals during traversal. Instead of manually reversing lists, we adjust the insertion direction dynamically during the traversal using a double-ended queue, or deque. This approach is more efficient and avoids the performance bottlenecks of the brute force method. The optimized approach leverages the properties of a deque to handle dynamic insertion efficiently. By alternating the insertion direction at each level, we can achieve the zigzag pattern without needing to reverse lists. For example, when traversing left to right, we append node values to the end of the temporary list, and when traversing right to left, we insert node values at the beginning of the list. This ensures that each level is correctly ordered in a single pass. The time complexity for this approach is O(n), as each node is processed exactly once, and all operations on the deque, such as append and insert, are performed in constant time. The space complexity remains O(n), accounting for the queue and temporary lists used during the traversal. This approach is not only more efficient but also simpler to implement and debug compared to the brute force method. Additionally, we considered an alternative recursive strategy using a depth-first search, or DFS. In this approach, we use a list of lists to represent each level, dynamically inserting values based on the direction of traversal. However, while the DFS method is elegant and has a similar time complexity of O(n), it introduces additional challenges. The recursion stack can grow significantly, especially in the case of deep or unbalanced trees, which may lead to stack overflow errors. Thus, while feasible, this method is less robust than the iterative approach. After evaluating the options, we chose the optimized approach that uses dynamic insertion with a DEEC during an iterative level order traversal. This strategy strikes the perfect balance between efficiency and simplicity. One key observation that guided this decision is that the zigzag pattern can be achieved using alternating insertion directions, which the DEEC handles seamlessly. The realization that we could completely avoid reversing lists was a major aha moment in this process. This approach has several advantages. It requires only a single traversal of the tree, ensuring O(n) time complexity. Its iterative nature makes it easier to understand and implement, especially for beginners, and it avoids the pitfalls of recursion depth issues. While the recursive DFS method is equally efficient in terms of time complexity, the iterative BFS approach is more practical for real-world use, as it minimizes the risk of stack overflow and is generally more intuitive to debug. On the other hand, the brute force approach was ruled out due to the unnecessary overhead of repeated list reversal, which makes it impractical for large trees. The recursive DFS approach, while elegant, has limitations that make it less suitable for this problem. The primary concern is its reliance on the recursion stack, which can lead to stack overflow in deep or unbalanced trees. This lack of robustness makes it less reliable compared to iterative solutions. Additionally, the DFS implementation can be harder to debug and maintain, especially for those who are less familiar with recursive algorithms. For these reasons, we decided against using the DFS method. Ultimately, the optimized iterative BFS approach with dynamic insertion using a DEEC emerged as the most efficient and practical solution. It is robust, easy to implement, and avoids the pitfalls associated with recursion depth. By leveraging the DEEC for dynamic insertion, we achieve a clean and efficient solution to the binary tree zigzag level order traversal problem, making it the clear choice for this task. Here, we're tasked with performing a zigzag level order traversal of a binary tree, which means traversing the tree level by level, but reversing the order of the node values on odd-numbered levels. To solve this, we use a brute force approach that leverages a queue for level order traversal. First, we initialize three key components: a queue to facilitate the traversal, starting with the root node, a result list to store the final output level by level, and a variable called level to track whether the current level is even or odd, beginning at 0. Next, we perform the traversal itself. While the queue is not empty, we process nodes one level at a time. For each level, we create an empty list called current_level to temporarily store the values of the nodes at that level. To ensure we process all nodes in the current level, we track the size of the queue at the start of the level, which we call level_size. This allows us to limit the number of iterations for that level, ensuring no extra nodes are processed prematurely. By following these preparatory steps, we set up the foundation for processing nodes at each level efficiently. Now, we focus on processing the nodes at the current level. For the number of iterations specified by level_size, we dequeue a node from the queue and append its value to the current_level list. If the dequeued node has left or right children, we enqueue these child nodes to ensure they are processed in subsequent levels. Once all nodes for the current level are processed, we check if the level is odd. If it is, we reverse the current_level list to align with the zigzag pattern required by the problem. Regardless of whether it's reversed or not, we append the current_level list to the result list. Finally, we increment the level variable to move on to the next level. After processing all levels, we simply return the result list as the output. This approach works well due to the properties of the queue, which ensures that nodes are processed in the correct order for each level. The reversal step for odd levels is what allows us to meet the problem's requirements. In terms of complexity, the algorithm is efficient. Each node is processed once, resulting in O(n) time complexity, where n is the total number of nodes. Reversing the list for odd levels adds a minor overhead but keeps the overall complexity at O, n. Spacewise, the queue holds nodes level by level, which means at most it will contain all the nodes from the largest level of the tree, resulting in O, n, space complexity in the worst case. To implement this solution, we rely on two key data structures, a queue and a list. The queue is pivotal for performing level order traversal, as it ensures nodes are processed in the correct sequence. The list serves as temporary storage for node values at each level before they are added to the final result. When handling edge cases, we must account for scenarios like an empty tree. If the root is null, we immediately return an empty list since there are no nodes to process. For a single node tree, there is only one level, so no reversal is needed, and the result is simply the value of the root node. Another important edge case is when all leaf nodes appear at an odd level. In such cases, we must ensure that only the values of the nodes at that level are reversed, not their positions within the tree structure. These considerations help ensure the algorithm is robust and handles a wide variety of input scenarios correctly. Let's walk through a specific example to see this algorithm in action. Consider the binary tree shown here, where the root node is 1, with two child nodes 2 and 3, and further levels include nodes 4, 5, 6, and 7. On level 0, which is even, we simply add the node value, 1, to the result list without any reversal. On level 1, which is odd, the node values, 2, 3, are reversed to 3, 2, before being added to the result, maintaining the zigzag order. Finally, on level 2, which is even, the node values, 4, 5, 6, 7, are added as they appear without reversal. The final output for this example is 1, 3, 2, 4, 5, 6, 7. To optimize further, we can skip reversing odd levels if there is only one node at that level, as no change would occur. Additionally, instead of constructing a separate list for current_level, we can append values directly to the result list in reverse order when needed, reducing the overhead of list manipulation. These optimizations ensure the solution is not only correct but also efficient for larger input trees. Here, we start by importing the deque from the collections module, which will help us manage the nodes in our traversal efficiently. Then, we define the treenode class, which represents the structure of each node in the binary tree. Each treenode has a value, a left child, and a right child, all of which are initialized in the constructor. Next, we define the zigzag level order method within the solution class. This method takes the root of the binary tree as its input. The first thing we do is check if the root is none. If it is, we simply return an empty list because there's no tree to traverse. After that, we initialize an empty list called result, which will store the final zigzag level order traversal. We also create a deque called queue, starting with the root node inside it, to help us process each level of the tree. Additionally, we define a Boolean variable left_to_right, initializing it to true, to keep track of the direction of traversal for each level. Now, we enter a while loop that continues as long as there are nodes in the queue. Inside this loop, we first determine the size of the current level using the length of the queue. We also create an empty list called level_nodes to store the values of the nodes at the current level. For each node in the current level, we use a for loop that runs level_size times. Inside the loop, we remove the first node from the queue using popleft and append its value to the level_nodes list. Then, we check if the node has a left child. If it does, we add it to the queue for processing in the next level. Similarly, we check if the node has a right child and add it to the queue if it exists. After processing all the nodes at the current level, we check the left_to_right variable. If the traversal direction is not left to right, we reverse the level_nodes list to match the zigzag pattern. Then, we add level_nodes to the result list, which keeps track of all levels. Finally, we toggle the left_to_right variable to switch the direction for the next level. Once the queue is empty, meaning we've processed all levels of the tree, we return the result list, which now contains the zigzag level order traversal of the binary tree. Here, we start by importing the necessary packages and defining our solution class. The main function we implement is zigzag level order, which takes the root of a binary tree as input and returns a list of lists, where each inner list contains the nodes at a specific level in the desired zigzag order. First, we handle the edge case where the tree is empty by returning an empty list. Next, we initialize our result list to store the final output, a queue to facilitate level order traversal, and a Boolean variable left to right to track the direction of traversal for each level. We then add the root node to the queue to begin the traversal. Inside the while loop, we process each level, starting by determining the number of nodes at the current level using the queue's size. We also create a temporary list, level nodes, to store the values of nodes at this level. For each node in the level, we dequeue it from the queue, add its value to level nodes, and enqueue its left and right children if they exist. After processing all nodes at the current level, we check the direction of traversal using the left to right flag. If it's false, meaning the direction for this level is right to left, we reverse the list of node values for the current level using collections.reverse. This ensures the zigzag pattern is maintained. Then, we add the level nodes list to our result list and toggle the direction for the next level by flipping the value of left to right. The while loop continues until all levels of the tree have been processed, at which point the result list contains the zigzag level order traversal of the tree. Finally, we return the result list as the output of the function. With the traversal logic complete, we now turn to the treenode class that represents the structure of each node in the binary tree. In the treenode class, we define three fields: val, which holds the value of the node, and left and right, which are references to the node's left and right children. The class includes a default constructor for creating an empty node, a constructor that initializes a node with a value, and a third constructor that sets the value as well as the left and right child references. This structure allows us to build and traverse binary trees efficiently. With the treenode and zigzag level order function fully implemented, our solution is complete, enabling us to perform a zigzag level order traversal on any binary tree passed as input. To start, we are given a simple binary tree with a root node of 1 and 2 children, 2 and 3. The goal is to traverse this tree in a zigzag level order. First, we initialize three components: an empty list called result to store the final output, a queue initialized with the root node to facilitate level by level traversal, and a left _to right flag set to true, indicating the traversal direction for the first level. At level 1, the queue contains only the root node, so the level size is 1. We initialize an empty list level _nodes to collect values for this level. We dequeue the root node, append its value, 1, to level _nodes, and then enqueue its children, 2 and 3. At the end of level 1, we append level _nodes, which is 1, to result, making it 1. Finally, we toggle the left _to right flag to false to reverse the direction for the next level. Moving to level 2, the queue now contains nodes 2 and 3, so the level size is 2. Again, we reset level _nodes to an empty list. We dequeue node 2, append its value to level _nodes, and then dequeue node 3, appending its value as well. At this point, level _nodes contains 2, 3. Since the left _to right flag is false, we reverse level _nodes, making it 3, 2, before appending it to result. This gives us 1, 3, 2. Finally, we toggle the flag back to true for the next level. After completing level 2, the queue is now empty, which means there are no more nodes to process. At this point, we return the result, which is 1, 3, 2. Now, let's examine a larger binary tree. This tree has a root node of 1, children 2 and 3, and additional nodes 4, 5, and 6 at deeper levels. The traversal process begins with the same initialization: an empty result, a queue containing the root node, and left _to right set to true. At level 1, the queue contains only the root node, so the level size is 1. We initialize level _nodes as an empty list, dequeue node 1, append its value to level _nodes, and enqueue its children, nodes 2 and 3. At the end of this level, level _nodes contains 1, which we append to result, making it 1. We then toggle the left _to right flag to false to reverse the direction for the next level. For level 2, the queue now contains nodes 2 and 3, so the level size is 2. We reset level _nodes to an empty list and process node 2 by dequeuing it, appending its value to level _nodes, and enqueuing its children, nodes 4 and 5. Next, we process node 3 by dequeuing it, appending its value to level _nodes, and enqueuing its child, node 6. At this point in level 2, level underscore nodes contains 2, 3. Since the left underscore to underscore right flag is false, we reverse level underscore nodes, making it 3, 2. We append this to result, updating it to 1, 3, 2. The left underscore to underscore right flag is then toggled back to true. Now at level 3, the queue contains nodes 4, 5, and 6, so the level size is 3. As before, we initialize level underscore nodes to an empty list. We process node 4 by dequeuing it and appending its value to level underscore nodes. Next, we process node 5 in the same way, followed by node 6. At this point, level underscore nodes contains 4, 5, 6, and since the left underscore to underscore right flag is true, we do not reverse the list. We append level underscore nodes to result, updating it to 1, 3, 2, 4, 5, 6. With the queue now empty, the traversal is complete. The final result for this larger tree is 1, 3, 2, 4, 5, 6. Finally, let's consider an edge case where the tree consists of just a single node with the value 1. We start with the usual initialization, result as an empty list, a queue containing the single node, and left underscore to underscore right set to true. At level 1, the queue contains only the root node, so the level size is 1. We initialize level underscore nodes as an empty list, dequeue node 1, and append its value to level underscore nodes. Since this node has no children, there's nothing to enqueue. We append level underscore nodes, which is 1, to result, making it 1. We then toggle the left underscore to underscore right flag to false, but with the queue now empty, the traversal is complete. The final result for this single node tree is 1. To summarize, the queue ensures that nodes are processed level by level, while the left underscore to underscore right flag determines whether nodes are appended in normal order or reversed. By reversing level underscore nodes for odd levels, we achieve the desired zigzag pattern in the output. To analyze the time complexity of the binary tree zigzag level order traversal, we first consider the traversal of all nodes. The algorithm performs a level order traversal, where each node is visited exactly once. For each node, we dequeue it from the queue, append its value to the level underscore nodes list, and check its left and right children. Since there are n nodes in the tree, this traversal step takes n time. Additionally, reversing the level underscore nodes list for alternate levels adds another component to the time complexity. The maximum size of the level underscore nodes list corresponds to the largest level of the tree, which can contain up to n nodes in the case of a complete binary tree. However, across all levels, the total number of elements reversed is still bounded by the total number of nodes n. This ensures that the total cost of reversing levels is also n. Combining these two operations, the overall time complexity of the algorithm is n plus n, which simplifies to n. Now, let's analyze the space complexity of the algorithm. First, consider the queue, which stores nodes of the current level being processed. The maximum size of the queue occurs when processing the largest level of the tree. In a complete binary tree, this largest level can contain approximately n/2 nodes, making the maximum size of the queue n in the worst case. Next, the result list, which stores the values of all nodes grouped by levels, requires n space since it holds one entry for every node in the tree. Additionally, the level underscore nodes list temporarily stores the values of nodes at each level. Its size is proportional to the number of nodes at the current level, which again is at most n in the worst case. Since the queue, result, and level underscore nodes are independent, the total space complexity is determined by the largest of these components. Therefore, the overall space complexity of the algorithm is n. To further understand the efficiency of the solution, let's compare it to a brute force approach. A naive method might involve traversing the tree and storing all nodes in a single list, then manually grouping nodes by levels and reversing alternate levels. This would introduce additional overhead for grouping and reversing, leading to a higher time complexity of n squared, in the worst case. In contrast, the optimized approach combines the level order traversal and reversing operations into a single pass, ensuring that the time complexity remains n. When we consider different scenarios, the best case occurs when the tree is empty, where the algorithm terminates immediately with an output of, requiring 1 time and space. In the average case, with a tree containing n nodes, the algorithm processes all nodes and uses O(n) time and O(n) space. For the worst case, such as a complete binary tree, the algorithm still operates in O(n) time and O(n) space, showcasing its efficiency across all cases. Finally, let's summarize the mathematical justification for the time and space complexity. Each node is added to the queue exactly once, processed once, and its value is appended to the level_nodes list once. This results in O(n) operations for n nodes. Reversing all levels, as explained earlier, contributes another O(n) operations. Together, the total time complexity is O(n). On the space complexity side, the queue, result, and level_nodes collectively use O(n) memory at their peak. These structures operate independently, meaning the total space usage is also O(n). This makes the algorithm highly efficient, as both its time and space complexities are optimized to O(n), ensuring it handles even large binary trees effectively. When solving the binary tree zigzag level order traversal problem, there are a few common mistakes you need to watch out for. First, a frequent issue is forgetting to reverse the nodes at odd-numbered levels. Since the problem explicitly requires reversing the order of nodes at these levels, skipping this step results in an incomplete solution. Another mistake is not properly resetting temporary data structures between levels. For example, if you're using a list to store nodes at the current level but fail to clear it before processing the next level, the list will accumulate nodes from previous levels, leading to incorrect results. Finally, it's important to handle edge cases correctly, such as when the tree is empty. Assuming the tree always has nodes and not checking for a null root can lead to null pointer exceptions or errors. These mistakes are easy to overlook but can derail your solution, so addressing them is crucial. Now, let's look at a couple more pitfalls. One is using an inefficient queue implementation. For instance, relying on multiple queues or overly nested loops during the traversal process can increase time and space complexity unnecessarily. Simplifying the queue logic ensures your solution remains optimal. Another common issue is overcomplicating the reversal logic. Instead of manually swapping nodes or using nested loops, which can be error-prone, you can leverage built-in methods like reverse in Python. This makes your code cleaner, reduces complexity, and minimizes the chance of logical errors. By focusing on efficiency and simplicity, you'll write more robust solutions while avoiding common traps. Understanding a few key insights can significantly improve your approach in both practice and interviews. For example, many level order traversal problems involve toggling a flag or using two queues to track levels. Recognizing this pattern is critical when dealing with variations like zigzag or spiral order traversals. Additionally, interviewers often evaluate your ability to optimize space usage without sacrificing clarity. For instance, they might prefer in-place techniques for reversing over creating additional data structures. Don't forget to ask clarifying questions about edge cases, such as handling an empty tree, a single-node tree, or a complete binary tree. Proactively addressing these scenarios demonstrates attention to detail. Lastly, tree traversal problems often follow similar patterns, like using a deque for double-ended operations or toggling flags. Identifying these patterns can help you tackle related problems more effectively, such as binary tree level order traversal or reverse level order traversal. Finally, let's explore some alternative approaches and their trade-offs. A recursive approach can simplify the logic, but it comes with the risk of stack overflow for very deep trees. Its space complexity depends on the height of the tree, so it's something to consider for large inputs. Using a deque instead of a list can be another alternative. It allows for O(1) insertion and removal from both ends, making it more efficient for large trees. You could also consider in-place node modification, which eliminates additional space usage. However, this can make the tree unusable for future operations, as reversing it back to its original state might not be straightforward. Finally, the two-queue approach, while simplifying the separation of levels, increases space usage compared to toggling flags within a single queue. Each of these methods has its strengths and limitations, so choosing the right one depends on the constraints and requirements of the specific problem you're solving. Great job! We've successfully broken down the binary tree zigzag level order traversal problem. Remember, alternating traversal directions and using the right data structures are key to solving this efficiently. Thanks for joining. Don't forget to like and subscribe for more coding tutorials. Keep practicing, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!